we're just going to do a bunch of review from this first unit to prepare for our exam on Thursday. We're going to start kind of at the very beginning when we were talking about chemical structures. So I'm going to put down a molecular formula. We're going to go C4H10O. And you're going to draw the Lewis structure. Try to give me 3 different molecules. All right, there's actually a total of 7 that you could draw that share that chemical formula there. But everybody just take a second and give me the Lewis structure for 3 different molecules that share that chemical formula. All right, so our hydrogens will fill in last. I'll put down that carbon backbone there. All right, so you may have come up with different examples than I have here. Most importantly, though, you'll know that your structure is correct. If your carbon has 4 bonds and 0 lone pairs, your hydrogens have 1 bond and 0 lone pairs. And what about oxygen? 2 bonds, 2 lone pairs. All right, so as long as your structure meets those criteria, you have a correct Lewis structure that matches our chemical formula here. All right, I actually tried to come up with a few. I feel like a lot of people would have gotten this one here. I tried to come up with some other ones that maybe you didn't think of. All right. But now we're going to take these Lewis structures, and everybody's going to take a second and turn them into bond line structures. All right, you can use mine or you can use yours, but we're going to practice converting our Lewis structures into bond line structures. Okay, so here are my three structures converted into those bond line structures. And what I want everybody to do to double check their structures is to go back and count your carbons. Each one should have 4 carbons. That is the best double check for your bond line structures, is to always go back and count carbons. All right, we can also note that for our bond line structure, our carbons are at those endpoints and intersections. Our hydrogens are also implied. They complete the octet of our carbon, but these heteroatoms and their hydrogens we had to explicitly represent in our bond line structures. All right, and we have an example of a heteroatom with its hydrogen, as well as one that is instead in the middle of our carbon chain here. All right, and the last type of structure that we're going to work on here is you're going to draw me the bond line structure from these condensed structural formulas here. Let's do one more. All right, so I'm going to kind of quietly go in and fill in. You guys can check your work. right, so we have these two different uses of these parentheses here. One to indicate a repeating unit, like my 6 CH2s that I have in this molecule here. And then the other use is when we have this polyatomic group sticking off of our main chain. All right, and this one down here, I drew, instead of as a zigzag, I drew it as a cross because we have our 4 carbons here, our 4 carbon-carbon bonds explicitly represented. So we want to space them out equally. If you also did it kind of more like this, that's cool too. All right, this is okay, this is okay. What we don't want to see would be something where you started out like this, and then this next one down here. That's not okay. All right, and when we start talking about what's called stereochemistry, we'll start thinking about the 3D structures, the geometry of these carbons. We'll see why this one right here is not a good representation of the shape of that molecule. All right, so we have our condensed structures that we turned into bond line structures. Hopefully at this point, these bond line structures are sort of no-brainer because, again, once we learned how to draw them, we just started using them immediately to start talking about acid-base reactions. Cool. All right, so now you're going to draw 2 bond line structures that correspond to the formula CH3O with a minus charge. Okay, so one of them we would put that formal charge on our oxygen, meaning that we have to have now 3 lone pairs and 1 bond. That's how oxygen has that formal charge of -1. Or I could put that formal charge on the carbon, giving it a lone pair and a minus charge. All right. We had a fancy name for these negatively charged carbons. What did we call those? Carbanions. Everybody take a second and now draw me. I specifically want the Lewis structure of a carbocation. All right, so I specifically wanted a Lewis structure because we need to see that for a carbocation, we have this incomplete octet, right? Their carbon should have 3 bonds and no lone pairs, so it only has 6 electrons in its octet, which is what leaves it with that positive formal charge. All right, sticking to this idea of formal charges here, I want you to draw an example of a structure with a positively charged oxygen and then one with a negatively charged nitrogen. You can put however many carbons you want. But I want that oxygen to have a formal charge of +1 and nitrogen to have a formal charge of -1. All right, so if we have a positively charged oxygen, that means that it should have 1 lone pair and 3 bonds. Put a hydrogen on there. So here's an example of a positively charged oxygen. If I'm going to do a negatively charged nitrogen, it needs how many lone pairs? 2 lone pairs and 2 bonds. Cool. So importantly, you could have given me a different structure than this, but we want 3 bonds, 1 lone pair. That's our bonding pattern for a positively charged oxygen. Likewise, 2 bonds and 2 lone pairs. That would be my negatively charged nitrogen. Cool. All right, so first thing we did in this course was we kind of introduced these ways of drawing these organic structures and talking about bonding patterns. First, what an element likes to have, right? Meaning that it has that formal charge of 0. But we also talked about how oftentimes when we're talking about chemical reactions, our atoms will adopt some sort of a formal charge, and we talked about our bonding patterns for that as well. All right, so then we started talking about electron pushing arrows. All right, and the first step was we learned how to follow them. Meaning I'm going to put down some structures with some electron pushing arrows, and you're going to draw me the result of that movement of electrons. All right, so we're seeing our bonding patterns again. I'm going to take this negatively charged oxygen. Okay, I want you to follow our electron pushing arrows, give me the result of this here. But I first want you to identify whether these are bond breaking, bond formation, or both breaking and formation arrows. All right, label each one of these electron pushing arrows according to one of those three categories. That's the best first step. Until you're really good at just seeing what these arrows are doing, if you're having trouble figuring out what these arrows are doing, step one is to put it into one of these three categories here, right? That'll help us figure out what exactly should be happening for each one of these. All right, so for this first one here, which category does that arrow belong to? This would be a braking arrow, so I'm going to color code these. So if this is a braking arrow, then where does this pair of electrons that is currently a bonding pair, what's it going to turn into on the product side? A lone pair, and specifically that lone pair we can see is going to be sitting on that chloride ion. So now we have our halogen bonding pattern of 4 lone pairs and that negative charge. And importantly, that extra lone pair used to be a bonding pair on my reactant side. All right, and what about the next arrow? What does this arrow represent? This would be a formation arrow here, which means I'm going to have a new bond. This lone pair here is going to become a bonding pair on the product side. Okay, so drawing that out here, I have my same 3 carbons, but now I have my new carbon-oxygen bond. All right, and importantly, this lone pair here is now my new carbon-oxygen bond on the left. All right, again, counting carbons, really important. So let's just kind of count carbons to convince ourselves. We have 1, 2, 3 carbons from this fragment, plus another 1, 2 from the other fragment. Again, counting carbons, very important, double check. Right? We can't be losing atoms. We can't be gaining any new atoms. Everything should be accounted for. Okay, same deal. So I'm going to put down a few more examples. You're going to follow those electron pushing arrows for me. And again, that first step, put them into those 2 categories, one of those 2 categories. All right, so for this one here, let's do this first one. This first arrow here, what category would I put that in? That's a breaking arrow, meaning that this bonding pair of electrons is going to become a lone pair on my product side. And what about the other arrow here? That one's a formation arrow, meaning that this lone pair is going to become a bonding pair. All right, so I'm going to space these out at 90 degrees. All right, and I'm missing some formal charges here. What am I going to need on my oxygen? That minus formal charge, because again, that bonding pair became a lone pair. So now I got 3, that extra lone pair on there. What about my nitrogen? Positive, negative, neutral. It's neutral, right? It used to have that negative charge, but now that pair of electrons became that bonding pair. So it's got its 3 bonds and its 1 lone pair. All right. For this example here, let's look first at this arrow. Which type of arrow is that? So that's a normal breaking arrow. But what about the other one? This is one of those break and form arrows. All right, we're going to turn this bonding pair into another bonding pair. It used to be a carbon-carbon bond. Now it's going to be a carbon-hydrogen bond on my product side. All right, and then my bromine has that extra lone pair, making it a bromide ion. And what am I missing? I'm missing a formal charge here. I know that because everything's neutral over here, but I have this minus sign over here, so I have to have a positive formal charge. Remember, when that double bond breaks, one of those carbons keeps that pair of electrons, forming that new carbon-hydrogen bond. The other one got that pair of electrons taken away from it, leaving it with that incomplete octet or that carbocation. All right. I've had this question a lot, so let me just be clear. A lot of students are like, well, which one should I put the hydrogen on? The one on the left or the one on the right? In this case, it's irrelevant because this molecule is symmetric. In fact, all examples that we've seen up until this point, it wouldn't have mattered because the molecules I specifically chose to be symmetric. Meaning if you put it over here, it'd be the exact same as if you put it over here, just kind of turned around. Okay? When we start studying these carbon-carbon double bonds, we're going to study these reactions and we'll totally have a logic as to where that positive charge goes and where that hydrogen goes. For right now, it doesn't matter. The important part is that one of those carbons gets the hydrogen, the other one gets the positive charge, right? That's the important thing that we need to have to make sure that our structure is correct. Okay? And when we study this reaction, we'll learn that this carbocation is actually an intermediate in this reaction. The reaction doesn't stop here. All right? The reaction would keep on going, and we would get this final product. So I want everybody to take a second and fill in the missing electron pushing arrows to get me here. All right, meaning you're going to take that intermediate and you're going to draw in that last electron pushing step that has to happen in order to get to our product here. All right, so if we look, I just need to form this new bond over here. So I'm going to put in a bond formation arrow I'm going to get rid of my color coding on this intermediate so we can be clear here. That's that lone pair on that bromine forming that new carbon-bromine bond. Cool. All right, another one that we're going to look at, another mechanism here. I lied. Let me put it here. All right, these alcohols will also react with these strong acids. All right, and I'm going to tell you that this first step here is an acid-base reaction. But I have this alcohol that can donate a proton, not a protein, and I have HBr that can donate a proton. Which one do we think is going to play the role of the acid? HBr. So, but how can we check? pKa's, right? So let's go and look up our pKa for HBr. Let me get rid of these real quick. HBr's got a pKa of -9. If we look at our alcohol, we can't find that exact alcohol, but we can note that alcohols typically, ethanol, methanol, OHs are around 15 to 16. All right, so we're going to go ahead and approximate that as 16. So we got a pKa of -9, a pKa of 16. So which one's our stronger acid? HBr, right? So if we didn't know, we could go ahead and look that up. So then everybody considering those pKa's, I want you to give me the product here, all right, and then fill in those electron pushing arrows. All right, this is my acid, this is my base. All right, so we're going to increase that number of hydrogens, increase that charge to get my conjugate acid. My bromide ion here. So our acid-base mechanism, we have one electron pushing arrow, that's a bond formation arrow. We have another electron pushing arrow, that's that bond breaking arrow. All right. How did I know that the oxygen in this molecule specifically was going to be playing the role of the base? Like, why didn't I protonate one of these carbons or something like that? So octet rule, I wouldn't be able to do that without breaking my octet rule. What other common feature do all bases have? Like, necessarily, if something's a base, it has to have a lone pair. right? That's always what's reaching out. We always need that bond formation arrow, meaning we have to start at a lone pair. So what you'll see, a common feature in all of your bases is in order to be a base, you have to have a lone pair. You have to be able to draw in that bond formation arrow. All right. And what if I want to know how efficient this first step is here? Meaning, which direction does my equilibrium lie in? All right, so I'm going to compare the pKa of my acid, this -9 here, to my conjugate acid. Going to our pKa table here, we'll find our protonated alcohols around -2.4. We're going to have to approximate it. We don't have the exact structure, but that's pretty good. Where was I? Okay. So what would we say about our equilibrium here? Which direction does this reaction favor, the products or the reactants? So first of all, if I'm going to compare HBr to my conjugate acid here, which one's the stronger acid? The HBr, the one with the lower pKa, right? So the stronger acid is going to win, meaning it's going to push the reaction in the other direction. So by determining which one's stronger, I can tell that this favors the products. And then what's that cutoff value that we use between weakly and strongly? That pKa difference of 3. So this would be one that strongly favors the products. Okay, so somebody had asked me, do I have to memorize that delta pKa formula? I don't think you have to memorize anything as long as you note that cutoff of 3, because you should be able to look and say whether it favors the products or the reactants just by classifying which one of these is the stronger acid. So if you want to go through and remember conjugate acid minus acid and then -3 versus positive, all that jazz, go for it, right? But I don't think you have to do all that. I think you should be able to logically take a step back and say, all right, this one's my stronger acid, meaning that it favors the products. It's going to push this in favor of the products. And then I just have to remember that difference of 3, whether it's greater than 3 or less than 3. All right, that's kind of the easy way to do it, rather than kind of memorizing math formulas here. So you do have to know strongly versus weakly, okay? And that, again, that difference being if the delta pKa is greater than 3, right? But I'm thinking in absolute value terms rather than memorizing -3 versus +3 kind of thing. Okay, so it turns out that this absolutely does happen. As we established, we can even figure out where our equilibrium lies. This isn't the end here. If we do mix an alcohol with HBr, there's one more step that occurs. I want you to put in these missing electron pushing arrows. This would not be an acid-base reaction. This is what we would call a substitution reaction. But everybody's going to take our intermediate here and fill in those missing electron pushing arrows. All right, so I have this one new bond that I need to form. I'm going to do my bond formation arrow. And then I have this bond here that I need to break. So I'm going to do my bond breaking arrow, turn that into a lone pair on that oxygen. All right, so again, another reaction that we'll study throughout the course of this semester. We do this first acid-base step using what we learned in chapter 2, and then I'm just telling you now, you wouldn't know this off the top of your head, but I'm telling you now that there's this other product, this other step that's going to happen, and we can fill in our missing electron pushing arrows to see the mechanism of this reaction. All right, so switching gears here into acid-base reactions. I'm going to put down a few acids, and you're going to rank them from strongest to weakest for me. You good? Put in my lone pairs. All right, so when I'm talking about the stability, I'm not, whoops, jumping ahead. When I'm talking about the strength of an acid, what we want to think about qualitatively is really the stability of the conjugate base. All right, so if I'm thinking about these acids and thinking about which one's going to be the strongest versus the weakest, really what I'm looking at are my conjugate bases. So I'm going to donate these protons here. Place them with that lone pair. And we're going to take a look. All right, and we have that acronym that we use to qualitatively compare these things here. What is that acronym? Fario. What's the F stand for? Formal charge. All right, so all of these here have this formal charge of negative. So is any one more stable than the other based on that F, that first category? No. Okay, so let's move on down the line here. What about atom? Is this going to help me distinguish between any of these here? So here we have our nitrogen versus these ones all have our oxygen. All right. So what are we comparing about these atoms that's going to tell us which one's more stable or less stable with this negative charge? Electronegativity. All right. So based on electronegativity, which is stronger, or rather, which is more stable, an oxygen with a negative charge or a nitrogen with a negative charge? Oxygen with a negative charge. So boom, right off the bat, we can say, all right, this has to be my weakest, let's say weakest. Weakest acid. All right, the other ones are all tied at the A, so now we're going to go on. R stands for resonance. Do any of these have resonance associated with them? Let's call them A, B, C, and D. Are any of them resonance stabilized? Which ones? A's got that allylic lone pair. C's got that allylic lone pair. So both A and C are resonance stabilized, which means that if I'm putting these in order from strongest to weakest here, my next one down the line here is going to be that alcohol. All right, actually I'm going to leave it like this. All right, so now I have to distinguish between A and C here. Which one of my letters in my acronym is going to help me out with that one? The I for induction. Which one of these is induction stabilized, A or C? C, because of that electronegative element. It's not right next door holding that charge. It's located these 2 carbons away, but nonetheless, through induction, that fluorine can help stabilize that negative charge. So next would be that acetic acid, followed by that fluoroacetic acid. That's my strongest out of those. Okay, we talked about resonance stabilization as one of these factors that go into the strength of our acid. Let's kind of pivot here and use that as an opportunity to talk about resonance. All right. Resonance, I've heard from some students that this was like one of the harder of the assignments, these resonance patterns, okay? So if I'm studying this here, I'm gonna remember that there are 4 resonance patterns, okay? And in order to make sure that I know what the heck's going on, I'm going to be able to recall what those 4 are, all right? That's gonna be my step, my advice to you in terms of learning resonance here is we have 4 categories, and we want to be able to recall them off the top of our head here. All right, that's how we're going to ensure that our brain is actually holding on to this information. So somebody give me one of them. What's one of our resonance categories? So we got an allylic lone pair. What's another one? Positive charge. So specifically, positive charge what? Carbocation, what about it? So carbocation by itself doesn't have resonance. Adjacent to, so there's two with carbocations, all right? One of them is going to have that fancy vocab word in there again, an allylic carbocation. All right, the other one is a carbocation next to or adjacent to a lone pair. All right, and look at these three categories here. They're kind of just like mixed and matched here. We have an allylic lone pair. Then we have an allylic carbocation. And then lastly, we have a lone pair next to a carbocation. So we got these three little vocab words being tossed around for each of those three categories. All right, just kind of mix and matched. What's the last one that I'm missing here? That pi bond between atoms of differing electronegativity. All right, great. Come up with an example for each of these four categories here. All right, draw me a structure that has an example from each of those four. Okay, so first of all, this vocab word allylic, we want to remember means neighboring, next door neighbor to that pi bond. All right, so this would be a lone pair in the allylic position here. All right, it's next door neighbor to that pi bond. Here's a carbocation next to a lone pair. And then I'm going to put that carbocation in that allylic position. Again, next door to a pi bond. All right, and then these carbonyls are a great example of that last resonance category. Remember, carbonyl is that special name we give to a carbon-oxygen double bond. All right, so here are my four categories. Again, if I'm studying resonance, I'm going to try to make sure that I can recall what those four categories are, and I can have an example for each one. That's how I'm going to study. All right, and for each one here, I gave you one resonance contributor. You're going to finish off this by giving me my other resonance contributor. so our allylic lone pair, sort of might want to note that this one is going to have 2 electron pushing arrows. Each of these other ones just have 1 electron pushing arrow. Kind of helpful to keep in mind. All right. That lone pair is going to come down into the p orbital of that pi bond. I need a second arrow though. I can't stop there or I would be breaking that carbon's octet. That pair of electrons needs to jump up onto that carbon. So I have both a bond formation and a bond breaking arrow in my allylic lone pair resonance here. All right, my carbocation adjacent to my lone pair. That lone pair goes into that empty orbital of our carbocation. So we have a bond formation arrow. Okay, in my allylic carbocation, that pi bond pair of electrons moves into that empty orbital of my carbocation. So which category of our resonance do we have here? Yeah, this is an example of a breaking and formation arrow here. Right, that bonding pair of electrons is now moving over, becoming a new carbon-carbon bond. Right, like with our other bond formation and breaking arrows, that's going to leave that other carbon with that incomplete octet. All right, and then lastly, with our pi bond between atoms of differing electronegativity, that more electronegative element pulls that electron density onto itself. All right, leaving us with a negative charge on our oxygen and a carbocation down below. All right, again, this carbon got that pair of electrons taken away from it. All right, so being able to recall what those 4 categories are is, step number 1, and then being able to draw an example from each one of those categories. That's step number 2 if I'm studying my resonance here. All right. Lastly, let's switch gears here and talk about base strength. Talked about acid strength. Let's talk about base strength. All right, so we got 3 bases here, and I want you to organize these from strongest to weakest. All right, and remember when we're talking about base strength, we're looking for which one is the least stable, right? The one that's the least stable is going to be the most likely to steal a hydrogen from somewhere else. All right, which one of these is the least stable? Let's call them A, B, C, and D, or just A, B, C. A, right? Nitrogen, being less electronegative than oxygen, is much more angry to have that negative charge. Okay, so that's our strongest base. What's the next one going to be, B or C? B, because C is nice and resonance stabilized, meaning that it's the most stable of those 3 structures. Cool. All right, and then lastly, let's take one of these bases. Let's do our full mechanism here for this acid-base reaction. All right. Hopefully we can tell just by looking at our structures here that this will play the role of the acid. This one will play the role of the base. All right, complete your mechanism by giving me the products as well as filling in our missing electron pushing arrows up top. So we always have that bond formation arrow and that bond breaking arrow for our mechanism. So my conjugate base will be that deprotonated oxygen. My conjugate acid will now be my protonated nitrogen. And we did this before, but again, let's figure out our equilibrium here. We're going to need to look up, let's just label these. All right, which two do I need to look up in order to figure out where my equilibrium lies? Both the acids, right? My acid and my conjugate acid. Importantly, my conjugate base, and sometimes my base might be on there if it has a donatable proton. In this case, even though there is that hydrogen on there that in theory could be donated, you would have a hell of a time getting it off because nitrogen's already very mad to have that -1 charge. It's definitely not going to donate that hydrogen and give it a -2 charge. So you actually wouldn't be able to find this one on there either. This one doesn't even have a donatable proton, so it's definitely not going to be on there. But yes, we're going to look up our two acids on our pKa table. All right. Somewhere in the middle, you should be able to find one of them. We got it? 2.7. Let's look carefully at these real quick. Fluoroacetic acid is 2.7, chloro 2.8, bromo 2.9, and iodo 3.2. So my strongest here out of these four is the fluoro, and the weaker one being the iodo. Why would that be? So in this case, when we were talking about size, that's why hydroiodic acid, the atom that's donating the proton, is when we were talking about size, right? So hydroiodic is the strongest, then hydrobromic. Over here, it's the opposite trend, right? Iodine is the weaker of them two, and fluorine is the stronger. But that's because these aren't atoms donating their hydrogen. They're stabilizing these acids through what? Induction, right? And remember, induction's all about electronegativity. So our most electronegative one is the best at stabilizing through induction. Iodine is less electronegative, so it's not as good as stabilizing through induction. Okay, anyways, just kind of poking around on this pKa table is pretty interesting. All right, and then the last one, I need that what we call methylamine. My pKa of 40. So one of, what did I say, 2.7? 2.7 and 40, okay. So this one is 2.7. My conjugate acid is 40. So which direction does our equilibrium lie? Products or reactants? Products. All right, my stronger acid is going to win. And in this case, does it strongly or weakly favor the products? Strongly. This has got a very strongly favors the products. Oops. All right, huge difference in pKa there. This would be a very efficient acid-base reaction here. Cool, and this is what we'd call our full mechanism, right? Not only do we have our balanced chemical equation with our acid base, and conjugate acid, but we also have our electron pushing arrows, and we can even take a look at our two acids and compare their pKa's to say which direction our equilibrium lies. Cool. All right. As a reminder,